This conference will now be recorded.
So good evening. Today we are starting a new chapter, that is atom or structures of atom. So this is 12th chapter in 12th standard in the NCERT textbook. So in this particular chapter, what we are going to discuss is the structure of atom, the very preliminary models of atoms, and then we will learn what is Bohr's model, like given by Niels Bohr, and we'll see how the energy levels are in hydrogen atom and hydrogen like atom, and how there are various spectra or spectral series coming up. So we'll start with introduction and then we'll learn what was the first atomic model, and today we'll learn up to alpha particle scattering experiments and its significant result, and probably the prediction of atomic structure or atomic model proposed by Rutherford. So let us start with introduction. So by 19th century, actually there were enough evidences to predict the atomic structure or hypothesize the atomic structure. Like 1897, British physicist J.J. Thomson, he carried out electric discharge experiment through rare gas. Okay, through rare gases, and he discovered that every element contain negatively charged particle, like the atoms of every element, like all the elements contain negatively charged particle which were named as electron later, and these electrons are identical in nature for all the atoms. Okay, so these electrons are identical in nature for all the atoms or various elements, atoms of various elements. So that was the thing, and but actually there is a problem, some problem in the screen. I have to, I think, restart. I'll just take 2 minutes. Just excuse me, because the slideshow is not happening actually.
This conference will now be recorded.
So very good evening to all. Today we are starting a new chapter entitled atoms. So in this particular chapter we will be learning about the atomic structure, like atoms contains nucleus and electrons, how they are distributed, and what is the possible structure those things we will be learning. So in the very beginning, there was no clear idea about the structures, but later on, gradually the atomic structure was like properly understood, and again we'll see to in this chapter that the quantum idea for the stationary orbit has been given by Niels Bohr about the atomic structure, but that is also not very final because the spherical model of atomic structure was taken. That is not very proper. So in your higher standard classes, you will be learning again that orbit can be elliptic, etc. And also in higher quantum mechanics, you will learn that there is no concept of orbit only. Okay. So anyway, today we'll see with 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 brief introduction. We'll start this chapter. First of all, we will learn what is the first atomic structure given by Thomson. Then later on, Rutherford had given planetary model of atomic structure, and finally Bohr had given the structure of atomic model, which is based on quantum idea for the stationary orbits. So today we'll learn Thomson's model of atomic structure and alpha particle scattering and its significant result, and what are the aspects in the Rutherford's atomic structure or atomic model. So let us start with a brief introduction. In 19th century, enough evidences were gathered to predict the atomic structure. Like in 1897, British physicist J.J. Thomson carried out famous experiment, electric discharge experiment through gases, and from there he discovered that atoms of various elements contain negatively charged particle which are called as electron. Obviously this electron name was given later, and these electrons are identical for all different elements or atoms. However, atoms are neutral in nature. Neutral. Atoms are neutral. So what is implied by this? That atoms are containing electrons. Again, electrons are negatively charged. Further, atoms are neutral in nature. So it implies that there must be equal number of positive charges as well inside the atoms. If there are 50 electrons in the atom, then there must be 50 positive charges in that, so that the atom will be neutral. So this is all right. So based on these observations, J.J. Thomson gave the or proposed the atomic structure, and that was the first atomic model. So according to that model, according to J.J. Thomson's atomic model, positive charges of the atom is uniformly distributed throughout the volume of an atom, and the volume atom was considered to be spherical in shape, and throughout the volume, like you can see here, throughout the volume, the positive charge, this color you can see. Okay, so this brown color, brown color sphere, it is saying that all the positive charges smeared out throughout the volume of this atom, spherical atom. And what else? Negatively charged electrons are embedded just like seeds in a watermelon. How seeds of watermelons are there? See, seeds of watermelon will be scattered, scattered. Okay, not smeared out. They are scattered here and there. Similarly, you look. These are the electrons. These are the electrons which are scattered. Okay, or embedded inside the positive charge of the atom. Embedded in it, just like watermelon. This model is even called palm and pudding model. Palm pudding model means what? If you have eaten sometime fruit cake, what is there? So in the base you have all items, but there will be fruits scattered here and there, embedded in the cake. Cake will not be throughout; it will be somewhere, just like seeds, watermelon seeds are scattered here and there, or embedded inside this uh, inside the watermelon. As you can see these seeds are compared to be electrons in the atom, and this part, the whole part is which we generally eat. So this part is compared to be positively charged sphere. As you can see, this is positively charged sphere. Okay, and these are just like seeds in the watermelon. So I hope you have understood. So the whole sphere is actually a positive charge. Throughout the volume there is positive charge. And this electronic charge or electrons are just scattered or distributed or embedded in this atom. Okay. So this is the first model proposed by J.J. Thomson for the structure of atom. But however, there were drawbacks. That means this model was not exactly true. This model was actually uh, people were people were thinking this to be true until 1911, but thereafter Rutherford will give a new model that will learn. But what are the drawbacks in Thomson's model? See, in Thomson's model, by Thomson's atomic model, there were few things which could not be explained. First thing is that it could not explain the origin of spectral lines. We'll see in the hydrogen spectra, there will be a series of lines like the Balmer series, Lyman, Balmer, then Paschen, bracket, font, like that. Okay, and the discrete lines are there. Bright discrete lines will be there. Okay, bright discrete lines. So according to this model, Thomson's model, energy was distributed, like energy could be released continuously, but we see discrete spectrum. How is it possible? So it could not explain the spectral lines or spectral series in case of hydrogen atom and other atoms. Not only that, it failed to explain the large angle scattering of alpha particle also. Okay, we'll discuss this point when we discuss alpha particle scattering. So what was large angle alpha particle scattering and how to explain it, we'll see in the Rutherford model. So this model, so Thomson's model, so in any model or any theory, whatever we see in the history of science, first we take some theory or some explanation as true, but when we see that particular theory or experiment or whatever could not explain many other phenomena, then we seek for a higher theory or higher model. So that is what happening. So Rutherford actually was a student, former student of Thomson. So Rutherford came back to Thomson's laboratory, and he was given a charge to carry out alpha particle scattering experiment. Alpha particle scattering experiment for what? To know the atomic structure. Okay, atomic structure. So he was leading this experiment, alpha particle scattering experiment, to know the atomic structure in Thomson's laboratory. So on the suggestion of Rutherford, his two associates, H. Geiger and E. Marsden was that time I think 20 or 21 is, or maybe less than that. He was very young guy. He even did not achieve his or earned his BSc degree by that time when he was involved in this experiment, alpha particle experiment. So on the suggestion of Rutherford, H. Geiger and E. Marsden, they had actually carried out alpha particle experiment. So learn that alpha particle experiment, but let me briefly tell you before going to that detailed experiment. So from alpha particle experiment, actually Rutherford could get almost a almost a correct idea about the structure of atom, and he has proposed planetary model atom. What is planetary model? Like we know, we have sun, okay, sun in the center, and planets like our Earth is revolving around it, okay. But this was in elliptical orbit. Rutherford took it spherical orbit. We'll see that in the. So let us first learn what is alpha particle scattering and its significant results, etc. Then we will go for learning his model. So as I said, E. Marsden. So it is Geiger and Marsden who had actually devised the experiment. So what was the experimental arrangement? You can look here. So alpha particle experiment, you might be asking what is alpha particle, sir? Alpha particle is helium nucleus, 2He4, mass is 4 and electronic charge is 2. That means it has 2 electrons and 2 protons. Electrons and 2 protons. Okay. So this is helium. Helium atom is called actually alpha particle. It has charge 2 and almost 4 times mass of electron. Okay, so in the experimental arrangement, Geiger and Marsden, they had used, see, alpha particle, we'll learn again in the nuclear chapter that alpha particle cannot be produced simply. Simply you cannot produce, you have to have radioactive element which can be spontaneously disintegrating and producing alpha, beta or gamma ray. Okay, so radioactive element, they have taken radioactive element. What is that? They took radioactive element bismuth 214, and it has atomic number almost, yeah, 83. So bismuth 214 and this is 83 atomic number. So that is the source of alpha particle, that this nucleus, bismuth nucleus will emit alpha particle. So this alpha particle then were collimated, okay, were collimated through, see this, you can see this is actually lead seal box. Actually this box is made of lead. Why it is made of lead? Because this alpha particle cannot penetrate the lead beyond certain thickness, so it was made of lead and the source of alpha particle were kept inside, okay. And when alpha particles are emitted, those alpha particles will be actually channelized, okay, or they will be having lead bricks over here like this, lead bricks, to collimate or to have a fine beam of alpha particle, fine beam, just like light beam. You have to have a fine beam of alpha particle. Okay, we got alpha particle beam. Then what? Then this you can see it is written gold foil. Gold foil, it is a very thin sheets of gold, very thin sheets of gold. How much thin it is? It is of the order of 10 to the power 7 meter. Such a thin gold sheet has been kept here, and that alpha particle which has been collimated to get a fine beam of alpha particle, that fine beam of alpha particle has been guided to bombard this or strike this thin foil of gold. So you might be asking a question, sir, why the gold foil was taken such a thin gold foil? Okay, very nice question. So this foil has been taken this much thin to ensure that these sheets, thin sheets of gold has only one layer of atom, only one atomic layer. Okay, if you see this is the front side of the, like this side, the behind there is no other layer like this, there is no other layer like this. So single layer of atoms will be there to ensure that such a thin gold foil has been taken, okay. And with that, so has been taken, and what has been done, alpha particle, as you know, the alpha particle scattering means collision, elastic collision you can say, or collision. So alpha particle goes all the way through this as a fine beam of alpha particle, they strike the gold foil, okay. After striking there, alpha particle may, see there are few possibilities, as you can see, I'll just clean everything. After striking the gold foil, see this alpha particle, beam of alpha particle goes like this, and see most of them, they passes through, actually see alpha particle has energy, kinetic energy, almost some 5 million electron volt. Mega electron volt means 10 to the power 6 electron volt. So 5 into 10 to the power 6, or maybe in the range of this much energy. So with this much energy, when it, this alpha particle comes and hits here gold foil, there can be few results which were observed. But before that, let me tell you, see, we are just collimating it, and obviously it is not possible to see the alpha particle in naked eyes. So after this collision or after this strike, what is happening to the alpha particle, we have to note that. So to note that, you look, this is a screen, this is called a screen, just like a film, just like your film. It is actually containing zinc sulfide. Okay, ZnS, zinc sulfide. That is a phosphorus material. Okay, phosphorus material. Okay, what does this do? As soon as electron or any high energy particle just strike the ZnS, the screen having ZnS or phosphorus material, it will create scintillation. Scintillation means they will create bright light. It will create as soon as the alpha particle goes and hit the screen. So this is actually called circular detector or screen. So you can understand after, see, you can just see the alpha particle after striking the gold foil where they go. If you can see bright light after reaching the screen, see here, they go and strike the screen. Okay, screen or this detector. So this is actually a circular detector. This is kind of a film. Okay, so film, like wherever your light goes and so that places there will be some reaction. So same thing happens here, wherever the alpha particle after passing through this gold foil hits the screen, there will be bright light, and just by seeing that bright light you can understand where are the alpha particles going scattering by after scattered by this gold foil or after the collision of this with this gold foil. Okay, I'll show you one more thing here. Look, so what was the main thing here? So this is experimental arrangement and this is how the experiment was done. But what are the parameters measured in this experiment? Look, the alpha source, these are the lead bricks as I showed. So they made a very intense beam with high energy, almost some 5 electron volt or 10 mega electron volt or 5 mega electron volt as I showed. And this is a thin gold foil as you can see here. So this is thin gold foil. So this is thin gold foil and this is actually the screen. So wherever there is a bright light that can be actually seen by a movable detector. See, these movable detectors can rotate up to 360 degree. As you can see, this is a movable detector or microscope with which sometimes naked eye we may not see the bright light or scintillation which was actually created by hitting, like out of hitting of the alpha particle to this phosphor material. So we can see that through microscope. So this is detector, movable detector or rotatable detector. It can rotate up to 360 degree. It can go up to here. It can go all the way up to here. So 360 degree rotation can be done for this detector. So with this detector, what we detect? We detect the alpha particle after passing through or after the scattering with this gold foil. And what were the observations we will see in the next slide. But let me tell you what are the possibilities. See, thin gold foil, as I said, there will be atoms, right? There will be atoms. Maybe there is a single layer of atoms, but see, alpha particles also are considered as particle, right? They have some dimension. So when they just go here, they will be actually, see, these are the atoms, right? These are the atoms. These are the gold atoms. So this alpha particle passes through, some alpha particle passes through the gold foil as you see here. Some alpha particles are scattering back here. Some alpha particle, very few alpha particle will be scattering just back. You can see some alpha particles are scattered at this angle. This is the angle called scattering angle. This is the initial direction. Initial direction is this. and this is initial direction, means direction at which it was coming, okay, from the source. That is the initial direction. And now where actually the alpha particle hitting the screen? Here. That means it has deflected. It has been deflected by this gold foil. So by how much angle? This much. This is called theta angle, and this is called angle of scattering or scattering angle. Scattering angle. So now the point is how many alpha particles are scattering at what angle? See, if I take this as 30-degree angle, so how many alpha particles are scattered at 30-degree angle? We can actually note down the data in that way. Like we'll rotate the detector at various angles. Maybe in your higher study you can do that. At various angle, we'll rotate up to 360 degree. We'll rotate at various angle and we'll see how many alpha particles are going and hitting over there at each and every angle. Maybe we'll start with 10 degree, then we'll go to 30 degree, then 50 degree. At each angle, we'll set this detector and see how many alpha particles are hitting over there. Okay? And then what has been done? See, we'll see in the next slide what has been done. See the number of alpha particles in this case. This is taken from NCERT textbook itself. So number of scattered particles are plotted against the scattering angle. So this is the demonstration of the experimental result. What we had done, we had counted number of scattered particles, scattered alpha particle at various angle, and then we have plotted the number of scattered alpha particle or detected alpha particle at various angle. See 0, 20, 30, 40 degree, 60 degree, 80, like that we have gone up to 180 degree. That means we started from this way, right? This is the angle 0 degree, and 180 degree means this way in the opposite direction, right? So this is the angle of scattering. Angle of scattering means suppose this is the direction of the alpha particle initial. After scattering the gold foil, at what angle it is deflected? That is called angle of scattering. So we'll see some particle will deflect, like various angle it will deflect. Very few particles will be deflected at 90 degree. Okay, at 90 degree. Maybe this is, let us take, very few particles will be deflected by 90 degree, like this. Very few particles will be deflected by 90 degree, and even a rare number of particles will be deflected by 180 degree. So those are the significant observations. What are those? Most of the alpha particle passes through straight through the gold foil, or in other words, most of the alpha particles suffer no deflection. Okay, suffer no deflection. So that's why we can see at 0 degree, that is the maximum alpha particle you see. 0 degree means what? So alpha particle doesn't get scattered. Most of the alpha particle detected here only. Okay, most of the alpha particle passes through. Deflection is not 0 deflection. Has most of the particle has 0 deflection. Okay. Then second thing is 1 out of 8,000 gets deflected by 90 degree. See, look here. Here maybe 90 degree. Okay. So this is 20. That means here. So this is 90 degree. Here is 90 degree. So this is 10 to the power 2. How many are there? Almost 10 to the power 7. And this is 10 to the power 2. So you look here, 10 to the power, if you take the ratio, so out of 10 to the power 7, you are getting how much? How many alpha particle you get here? Some 100 alpha particles you see, like see at 90 degree angle. So very few out of 10 lakhs, 10 lakhs, okay, 10 lakhs means 1 million. Out of 1 million, you see some 100, okay, some 100 getting scattered at 90-degree angle, okay. That means very few particles are see scattered in this direction. It is the initial direction, so this is 90-degree, right? So very few particles are scattered. So it is said that one out of 8,000 particles, alpha particles, are detected here at 90-degree angle. And occasionally alpha particle gets rebounded. That means rebound means what? It was going in this direction, it just come back in the opposite direction, exactly 180-degree opposite. That is called rebounded. So very few, occasionally alpha particle gets rebounded from the gold foil, suffering 180-degree deflection. So these are the few significant like observations in this experiment. I'll just take another 2-3 minutes because I thought of finishing the experiment, at least experimental part. Let us finish, then we'll stop here. See the significant results of alpha particle scattering and its possible explanation what Rutherford gave. So what we have seen, so most of the alpha particle were passing through. That means you look, this is the atom, and see most of the alpha particle is getting scattered. See what was Thomson's model? There were electrons scattered like this, right? Electrons scattered like this, and throughout there is positive charge. Okay, that means if really it is like everywhere there is positive charge, everywhere, if the positive charge is made out throughout the volume or distributed throughout the volume, then alpha particle also, it is having two electronic charge. This is also positive. Then what would have happened if this is the structure? See alpha particle, see thin foil will be having like atoms, gold atoms, right? Which has almost Z atomic number 29, sorry 79 almost. Okay, so it would have happened that alpha particle cannot reach even up to this gold foil. Okay, cannot reach if it is having positive charges distributed all over the volume. Okay, so rather what we have seen, that we are seeing that most of the alpha particles are just passing through. So why is it so? It is so because the most of the spaces, so Rutherford actually concluded that most of the space of atom, or most of the space inside atom is vacant. Okay, okay, or empty, we can say. Most of the spaces inside the atom is empty or vacant. Okay, that's why almost all the alpha particles are just passing through without any deflection. Okay, then what about the second observation, 90-degree? See, maybe some are getting deflected by some. See, if alpha particle, actually, see, alpha particle has two positive electronic charges. So only if there is positive charge particles inside the atom somewhere, then only it will be getting deflected. Okay, getting deflected, isn't it? According to electrostatic repulsion, positive charge, both positive charges will be actually repelling each other, then there will be deflection of the path. See, if I have a positive particle over here and I have another positive particle which is in motion in this direction, what will this particle do if the velocity is like this way? See, it will not go up to here, it will just be repelled by this positive charge particle and it will go like this. Okay, this is the way, or maybe in this way itself it will go. Here also it will go like this because it will be repelled by positive charge particle. So the deflection is happening actually due to the positive charge particle, because alpha is positive charge particle. Alpha is 2He4. So it is having positive charge. So when the alpha particles are actually getting deflected, you have to understand that they are repelled by positive charge particle inside the atom. So and so 90 degree, we have seen that very few particles are actually getting deflected by 90 degree. That means the size of the or spread of the positive charge particle is very very less. And the surprising thing is that occasionally one or two or maybe more, very very less possibility is there to getting rebound. That means alpha particle coming in this way and getting going, so coming with velocity v and going back with velocity v like this. Okay, it is going back in the opposite direction or getting rebounded. Very few particles. That means, see, the positive charge particle is actually distributed or kept at very very tiny space inside the atom. So from these observations, Rutherford actually made few conclusions or important comments on that, that as most of the alpha particle passes straight through the foil, so most of the space within the atoms must be empty. And to explain the large angle scattering of alpha particle, Rutherford suggested that all positive charges and mass of the atom is concentrated at very very small or tiny region called nucleus. So what is the outcome? Outcome is that, so I have said that most of the space empty first. So large angle scattering actually gives the hints of nucleus. That means most of the charges and mass of the atom is concentrated at a very tiny space called nucleus. Okay, and the nucleus is surrounded by a cloud of. So the third conclusion or comment Rutherford gave that the nucleus is surrounded by cloud of electrons whose total negative charge is exactly equal to the total positive charge on the nucleus, so that atom as a whole is electrically neutral. So what was the third conclusion? That nucleus is surrounded. So we have nucleus at very very tiny space, very very tiny, it has very very small radius. We'll see that in the next day. Very very tiny space, there is very very tiny nucleus where the whole the positive charge and the mass of the atom is concentrated, and electron clouds actually surrounding this nucleus. The nucleus is surrounded by, so third was nucleus, sorry, nucleus is surrounded by a cloud of electrons. And what is the charge of this cloud? Cloud has, if suppose the positive charge has one positive charge, so here the cloud of the electron also will be having one negative charge, such that they will, as a whole, the atom will be neutral. So from the significance, see, from these observations, like all the particle passes through, that means empty. Most of the space of the atom is empty. Large angle scattering gives the idea of nucleus. So Rutherford actually discovered the nucleus in the atom, and this is actually so nucleus, and also he had given the model, planetary model of atomic, sorry, planetary model of atomic structure. So what was that? That the nucleus is sitting at the center, and the electrons are actually orbiting around the nucleus at various orbit. So we'll see that in the next class, and obviously we will be learning, like we'll be calculating the possible size of the nucleus from Rutherford's experiment. There is something called distance of closest approach. Okay, and also we'll see Rutherford's predictions about the atomic structure, and what were the possible drawbacks, and if possible we'll take Bohr's model also on the next day. Okay, so I'll stop it here. Okay, bye for today.